Okay, so today we're going to solve the Schrödinger equation for a free particle. What do we mean by a free particle? Well, we've got a particle of mass m, and it's moving in a region of space with constant potential, and if it's constant, we'll set it equal to 0. So we're just going to say the potential is equal to 0 everywhere, and we're just moving in one direction, z. Postulate 5 tells us that solving the Schrödinger equation will provide a complete description of the system and how it develops in time. Therefore, we should get very used to this following procedure. First, write out a complete Hamiltonian for the system. Second, write down the Schrödinger equation. Third, solve the Schrödinger equation for the wave functions. And fourth, brew coffee, interpret the results, and publish them. Now, we're not going to do anything that groundbreaking today, so we're going to concentrate on the first 3 steps, right? So first, we're going to write down our Hamiltonian operator. H hat, of course, for the operator, is equal to a kinetic energy plus a potential energy operator, all right? We already said potential is equal to 0. We can drop that, but the kinetic energy part always looks the same. H bar squared over 2m times the second derivative with respect to x squared. Next, we're going to substitute that into the Schrödinger equation. And then third, we find the wave function. Well, looking at this particularly simple example, we can guess what the wave function will be. So we'll start with a trial wave function, then we'll see whether it works or not, right? Our trial wave function is going to be simply a normalization constant that's a little difficult to define for a free particle, but we don't have to worry about that. So let's just say a constant out front of an exponential term in I, K, X, so it's an imaginary term, right? Okay, then we need to actually solve the Schrödinger equation. We do that by substituting this wave function in and operating on it with that operator, kinetic energy operator, right? So we need to find the second derivative of the wave function. The second derivative of psi with respect to x squared is equal to, there's that first derivative, just look at the n that comes through, right? We'll need to take a second derivative as well, but the first derivative was just ikx. Remember, just bring that down there. E to the ikx, right? There we go. And then we'll have to take the derivative again. So we'll get another ik. I is just the square root of -1, so I squared is -1. So if we look at the second derivative of our wave function with respect to x squared, we're going to end up with the result minus k squared n e to the I kx. Confirming indeed, right, because here's our original wave function. And we just have a constant times that. So we did indeed prove that our wave function, our trial wave function, turns out to be a good wave function. It is an eigenfunction of the Hamiltonian operator because when we operated on it with the Hamiltonian, we ended up with a constant times the original function. All right? H operating on psi is equal to E psi. Oh, so that constant out front here must be equal to the energy, right? So let's now do the full Hamiltonian. Operating on psi will be minus h bar squared over 2m times that second derivative of psi with respect to x squared. Substitute in from our second derivative, multiply by minus h bar squared over 2, and we'll see that h psi is equal to h bar squared k squared over 2m times our initial wave function. Order of operation is important. Operate first, get your answer, then you can get rid of the psi. We see that this has got to be equal to E psi in other words, the constant out front here, is equal to the energy. Energy is equal to h bar k, that quantity squared, over 2m. All right? So now, if we were going to plot the energy versus x, or it turns out even versus time, what we'd find is, oh yeah, the 0, right, is set by the potential down there, and anything above that is allowed. Notice that we had no confinement. There's no confinement from the potential, and therefore the energy we got is a continuous function, right? There's no restriction on k, can take on any value, continuous values. So the energy can take on any value as well. So we've used the methods of quantum mechanics, but we got what essentially is a classical answer. An unconfined particle can take on any kinetic energy. It has a continuous distribution. In fact, this is going to be a very important result. We need a confining potential to cause quantization.